let us continue our discussion on the nature of light. So, in this particular class, we are going to discuss the nature of light from a particle point of view, where light will behave as a particle. Now, obviously, the question comes that why there was a requirement to discuss light as a particle, the quanta of light or photons, why there was a requirement. Life was good with waves. We have described several properties of light, interference, diffractions. So, why there is a requirement to go and return, so like a full circle when Newton described light as corpuscular theory, why we need to discuss or why we need to describe light from a particle point of view. Well, the answer was, I remember I told you that there were few gaps remaining in the line of physics, which the physicists were still unable to understand, these pockets that they thought that once we fill it, physics will end. One such topic was the gap which the wave nature of light could not describe, was photoelectric effect. Photoelectric effect, in which you bombard a surface of a material with light, and when the energy of the light reaches a particular threshold, electrons could be ejected from the surface and you can see electric current flowing or effect of that nature. The significant point here is that only when light of a particular frequency, particular energy, a particular specific threshold is crossed, this phenomenon is observed. Prior to that, if you have shown light onto this material surface of a very high intensity for a very long period of time, but still the energy of the light is less, if the threshold, the frequency of the light is less, no matter how intense your light beam is, no matter how long you have shown it, there will be no ejection of electron. Now, this fall flat on the topic of wave nature, because if you are shining light for a long period of time, a very high intensity of light, surely the wave should build up, constructive interference, it will go on happening and happening, building and building. At one point of time, the threshold will be reached and the electrons will be ejected. But no matter how long you have shown that light onto the surface, if the energy, if the frequency of the light is below a particular threshold, no effect is seen. Einstein described this effect by taking the cue from Max Planck, who has described that light comes in specific particles, specific quanta, and these quantas have a specific frequency, and thereby utilizing all of this, he described that it was the photon nature, the particle nature of light that was bombarding, that was passing its energy as well as its momentum onto the electrons that are present on the surface, resulting in the ejection of the electron from the surface. A threshold needs to be covered. Several other effects have also been encountered, which could not be described completely from a wave nature of light. Say for example, Compton effect, when light was interacting with a charged particle, say for example electron, the overall, after the interaction, after the collision had happened between light and the charged particle electron, the frequency of light has reduced. Reverse Compton effect is also shown, where the frequency of light has increased, the energy of light has increased. Several times a charged particle is encountering, or it is passing through a light field, is passing through an electromagnetic wave field, and there is no change whatsoever. Neither the electron is getting energized, nor there is much of a difference in the wave per se. All of these things could not be described by simply the wave nature of light. Therefore, we need to describe, or we required a different definition, a different explanation. That explanation was given by the particle nature of light, in which we described that light is also a particle. The particle of light is called photon, and that photon interact with matter and impart energy as well as momentum. This momentum is quite important. The momentum overall gives rise to direction, and although several topics of the photon, several nature of the photon is very similar to that of the wave, say for example, the wave vector. However, this is the fundamental aspect in which we describe that the energy of each photon is discrete. They are lumped together and they have specific value. So, E happens to be h and nu 1, E 2 happens to be h nu 2, and so on and so forth. Meaning that the different photons, different particles will have specific frequencies and thereby specific energy. There is a gap between E1 and E2, there is a discrete difference between E1 and E2, it is not continuous, there is no such thing as E1.1 or E1.25 as such. It has to be E1, E2, E3 because it is nu 1, nu 2, nu 3 as such. Anyways, several other topics came up. For example, photon carries a momentum which is given by this particular formula, and there is a spin, meaning the photon has a rotation on its axis. Whenever photons interact with electrons, this spin momentum is quite significant. Even if the spin is quite different, the electron might not be able to absorb the particular photon and gets energized. We have been discussing about photon from almost 100 years by now. Almost 100 years have passed when we have been discussing about photons. It could very well be said that the amount we knew before, when photon was discovered, was much larger than the information that we have about photons now. So, I will give you a description of what people thought about photon in the early stage. Please go ahead and read this ultra famous, very famous quotation. Okay. All the 50 years of conscious brooding have brought me no closer, to answer the question, what are light quanta? Basically, what exactly are photons? Of course, today every rascal thinks he knows the answer, but at the end of the day he is deluding himself. You know who said that? It was said by Albert Einstein, the gentleman who got Nobel Prize, or one of the greatest scientists who got Nobel Prize for photoelectric effect and describing how these things are happening. But this was in the year when 1950s or such, as such. Recently, this is the paper that you can refer to. Look at the year here, 2020, where in this particular paper, Results in Physics, they are still trying to ascertain if photon have a mass or not. I have purposefully avoided going into the direction of mass or photon or the spin of photon, because it will deviate us from the topic of biophotonics to quantum mechanics. But still the year 2020, we are discussing about the rest mass of photon, and if you can read the highlighted part, it starts with the behavior of photon is strange, it possesses both wave and particle nature. Some experiment shows both behaviors existing simultaneously, while some experiments state that both properties cannot exist simultaneously. So, what is it? In the year 2020, we are still unsure about it. Previously, we have discussed, or we have understood, or we have thought that light waves have no effect on gravity, and photons in general are massless, chargeless particle that moves around. Well, very recent experiments reveal that it has a non-zero value. Light or photon particles have a non-zero value. Then there is the topic of rest mass, imaginary rest mass. Several new things are coming up, and if you want to know, I ask you to explore the topic of quantum physics rather than the topic of biophotonics to understand the nature of electromagnetism or the nature of light in general. Okay. For the time being, read about what Albert Einstein said more about the nature of light and quanta. Nevertheless, despite the given fact that we have not fully comprehended what light is, whether it is wave or whether it is particle, it is fashionable to say it is both, but Richard Feynman tries to describe it as it is neither. Light is neither wave nor particle, but there is a small problem with this definition. When anybody says that it is neither this nor that, then the counter question comes, then what it is? And to be frank, I do not have the answer. I do not know what light is, whether it is wave or whether it is matter, whether it is both light and wave and matter simultaneously, or it is only one at a time. I do not know. And before you switch off this course thinking that your professor is rubbish, remember what Albert Einstein just said. He had no idea till the end of his life as well. And if Einstein can say he does not know, I can very well say that I do not know either. So, despite the fact that we do not know entirely about the nature of light or the nature of photon, it has not prevented us from developing the topic of photonics. And that is the most significant part. We do not need to understand something comprehensively to use it. Consider yourself the example of mobile phone or computers. Several people from different educational background, different societal background these days utilizes mobile phones or computers. Though very few people actually know the inner working of a mobile phone. Do you think every single person who uses a mobile phone understand the entirety of the process, how it is connecting, how it is wirelessly connected, what is happening inside, or for example, what is exactly happening inside the computer CPU, the algorithms being done, but it has not prevented us from utilizing it. Several drives a car, but how many people actually know the mechanical properties, the combustion engine properties that goes inside the car. So, technology does not require for a particular field to comprehensively developed. Technology and science can go side by side, and using whatsoever meager information we already have about this particular area, this particular field, we can utilize technologies to it. And it has been many times observed, many times seen that the technology is helping you understand what this particular field, what this particular subject is. Photonics is one such technology. Granted, we do not fully comprehend what photons are. It has not prevented us from utilizing photons for several different applications though. And why we should stop? We cannot wait that we need to fully understand what photons is and then only technology come up. The technology can start simultaneously, parallelly, side by side with whatever meager information we have, and that gave rise to the field of photonics. Photonics simply is control of photons in free space of matter. Electronics is the control of electrons, control of photons in free space or in matter is basically what photonics is. The idea is, though we do not want to discuss the mass of photon in this particular class, this is not a course on electromagnetism, neither is a course on quantum mechanics, but since the mass of photon is quite less, previously it was considered 0, nowadays they are considered it as a less, but not specifically 0 value. Since its mass is less, it can oscillate much faster than electrons, and thereby you can pack more amount of information to it. So, small photons, say a green light of 500 nanometer can carry this much amount of energy, whereas electrons will require a 2.5 volt battery to produce the same energy. So, photons are faster, they have more energy, they have large frequency, all of these things. So, engineers at Bell Laboratories USA, they use the term photonics. We already knew what photons were, Bell Laboratory engineers certainly did, and they thought that it will be better if we coin a new term, photonics, in which we utilize photons or light technology for several different applications. What is the difference of photonics with respect to conventional optics? This question comes up all the time, that we already knew about light by the end of 18th century or early 19th century. Even with the particle nature, we have utilized optics for a long period of time. We have magnifying glasses, we have microscope, we have telescope. Galileo have developed telescope. So, how are photonics technologies or the field of photonics in general different from the topic of optics? Well, to be frank, though the boundary has been breached, though the boundary is no longer that much rigid or that much valid, from a historical point of view, conventional optics utilizes 10 to the power 10 photons per centimeter square per second, whereas photonics is almost double that of the number. So, you could say that photonics utilizes more amount of photons. This amount is much large. There are more amount of photons per unit area per second. However, that boundary is regularly being breached. This is just a historical perspective. We make photonic integrated circuit, probably you will learn it at a later stage, where the photon count keeps on modifying, keeps on changing, and no one will say that up till this part this is photonics, then it has become optics, and then it is becoming photonics again. So, from a historical point of view, the difference between photons and conventional optics is the amount of photons, but overall it is not a very strict rigid boundary. Secondly, photonics basically deals with non-linear interaction between light and matter. Non-linear means where there is not a linear or there is not a straightforward. If x is directly proportional to y or x is inversely proportional to y, these are basically linear terms. But if x is equal to or say y is equal to ax square plus bx plus c, some kind of a complex relationship, we can very well say that this is a non-linear phenomenon. So, non-linear phenomenon describes, say, how light is interacting with electrons, how the electrons are getting are colliding with photons. We described spectroscopy, we described fluorescence per se, several non-straightforward matter, not straightforward matter are the purview or the realm of photonics, where optics mostly deals with reflection, refraction, just straightforward nature. And obviously, by using photonics, optical communication for example, fiber optics based systems, you have a speed of communication increased almost 100-fold. You all must be watching Netflix at home, or you have live streamed videos, high quality, etc. How do you think that have been possible? You have an optical fiber cable that can stream light which contains information. Remember the wave packet that I described in group velocity. So, the speed of communication has strongly increased as compared to the wired copper wire based communication that we used to have at earlier stages, which used to describe information. So, what are the different applications of photonics? Since we are discussing about biophotonics, it but natural that we describe little bit about photonics as well. So, there are several aspects of photonics. You have communication, of course, you can store information in the form of light, you have transmission, you have display, you can utilize lasers, which are an integral part of photonics for lithography, material processing, cutting and welding. You can utilize photonics, you can utilize light intense photons for biological imaging, light therapy, disease diagnostics, and obviously for several different things such as remote sensing, spectroscopy, etc. Now, please tell me, by this time you have understood which part of photonics we will be mostly discussing. This course, for all intent and purpose, will be focusing itself on this matter, where photons will be utilized to describe biological material. So, that is more or less the end of our course. These are the references, but before I let you go, I have two basic questions for you. Okay, these are not part of the assignment. This is for you to exercise your mind in, read about it a little bit, and maybe you will get interested. So, first question, usually photons are considered as massless and chargeless. Forget about the mass, for the time being considered photons are chargeless particle. Light is a neutral particle, right? Light does not have any charge. But if we describe a light which is moving in this particular direction with an electric field in this direction and the magnetic field in this direction, light is moving in this direction, this is x, this is z, and this is y. It has an electric field and a magnetic field. So, how come it is chargeless? It has an electric field, electric fields have their values, and it has a magnetic field as well. So, how come photons are chargeless? Number one question for me. Number two question, if there is a magnetic field, okay, can we not have a magnet in our hand and simply suck, simply attract this wave towards this magnet? So, consider this as a photon, photon has an electric field and a magnetic field. I have a magnet like this. Can I not attract like you attract an iron particle with a very strong magnet towards it? Can you not attract a magnetic field from light using a magnet? You have been seeing this image since I do not know middle school. Okay? There is an electric field hand, a magnetic field hand. So, if there is a magnetic field hand, we use a magnet to attract it. Okay, the magnetic field is oscillating. We use a oscillating magnet as well. You know, electromagnets, they can oscillate, they can give a south pole at one direction, north pole in one direction. We rotate the magnet. So, if we constantly rotate the magnet at a speed matching that is the speed of the light, speed of the photon, can we not? Can we not simply attract light towards this magnet? Imagine how beautiful our life would be. We will have a magnet, photon particle will be sticking to it, and after some time it will start emanating light, but we do not see that happening. Can you tell me why? Remember, this is not part of an assignment. This is also not particularly part of biophotonics. In biophotonics, we are going to discuss how to detect diseases, right? So, Maxwell's equations or the mass of photon, or for example, these two questions that I asked have very little consequences, very little relevance. So, I am not going to discuss that in detail. But if you are interested, try to think about it. Try to think about it that perhaps a little bit more depth on the already known topic, something which we have already discussed, probably is required, because some very important things can be lying in plain sight, which we have thus far only ignored. So, this basically ends my topic on the first module. This was merely the introduction. I know physics students will not be very happy because I have not gone to the entire depth of light and quantum mechanics, but I want to go as soon as possible into the heart of the matter, and that is how to image or how to see biological matter with light. For the time being, the information that we have on light will suffice. This was just to refresh you, so that next time when I use topics like refraction or diffraction limit, this light in under microscope is diffraction limited, you will be able to recall what diffraction basically is and what constructive interference is, things like that. Anyways, please drop below on the comment box what you think, what I should change, what I should keep, and any feedback, as long as it is constructive, is welcome. Thank you very much.